There, that's better. I was saying last time some people might like the idea of making like an object for your chromosomes that also stores the fitness. For me, for simplicity, I'm just going to store the population in a list, and I'm also going to store the fitness of the population in a list where the values at each index corresponds to the chromosome at that same index in the population. So far, so good? If you're looking at it, it's going like, yeah, this is simple stuff. Great. If you're not, let me know, because it should be simple. You're probably overthinking. So selection. We did this last time too, tournament selection, right? We talked about it? I think so. So this is the idea that we don't always want to pick the best one. We want to favor picking better ones. We want those that are better, that have a better fitness, to be more likely to be selected. But we don't want to just have always picking the best. Because if we do, we're going to destroy diversity in the population, which is going to be bad for the whole population. Although we're evolving individuals in the sense that we want the candidate solution with the best result in the end, it's the population that evolves together. So we have to be population-minded, not individual-minded. So how are we going to do it? Well, this might look sophisticated. It's not. I wrote this. If you go to the pie chart and you go to the selection, there's only 2 in there. Can you see reasonably well? Is this viewable? Too small? It's kind of small, right? All right, I'll do that later just because it's a pain. But yeah, bigger would be a little nicer. So all it's doing is it's taking the list of the population fitnesses, the selected indices. So we need to select some number of indices. So let's say I want to pick 2 randomly, and then the best of those 2 is selected. Maybe I want to pick 7 randomly, and the best of those 7 is the one that's selected. Whatever, I can play with that all I want. It's a hyperparameter. And then direction, that was just a way of saying, well, is this a minimization or a maximization problem? By default, it assumes it's maximization. If you put in a -1 here, I mean, you could put in a negative whatever. All it really matters is it's a negative number. It'll assume it's a minimization problem. Smaller numbers are better. All of this is just exception checks. The rest, this right here, it's just a linear search. For the indices you selected, search through their fitnesses, and whichever one has the best fitness, that's the one you return. That's all. That's all this is doing. If it looks complex, it's because I tried to make it verbose. But of course, calling selection once only selects one. We need to select many. We need to select the number that would fill a whole new population. If I have a population of 100, I would need to call tournament selection 100 times to select 100 new candidate solutions. It's possible that the exact same candidate solution is selected multiple times to be copied over. Fine, that's normal. Some might not get copied, that happens. The best one in the population might not actually even get copied. That's fine, it happens sometimes. But as you could probably imagine, as the number of candidate solutions in the tournament, if the tournament size gets bigger and bigger and bigger, we're going to be more likely to pick the best solution. Let me put it this way. If I have a population of 100 and my tournament size is 2, I pick 2. I'm not very likely to pick the best of the 100, right? So I pick 2 and I take the best of the 2. I'm probably not picking the best of the 100. As K gets bigger, as the tournament size gets bigger, if I cranked it all the way up to 100, okay, I have a population of 100. Of those 100, take the best. Well, that's just going to be the best one in the population, right? Now, when randomly selecting with choices, it's possible that that actually still doesn't happen because it is technically possible for choices to return the selected chromosomes all being chromosome at index 17. It's possible, it's not very likely, but it is possible. But the point is, as K gets bigger and bigger and bigger and bigger, you're more likely to increase selection pressure, which means you're more likely to always just favor those that are better. As K gets smaller, it's the opposite. You're more likely to not pick the best one. You're still going to pick those that are relatively good, but you're going to have more diversity in your population if this is low. Yeah?
So tournament size is like how many, like the two, like pairing, not how many times you run the tournament?
No. So that's a good question. No. The number of times we run the tournament is going to be once for each member of the population to fill a whole new population. The tournament is, okay, I've got a population of 100. Pick 2 of that. Which one's better? This one. Okay, I picked 1 now. Do it again. And so on and so on and so on. You'll notice here I made a new list called mating pool. I called it mating pool. Really, this is like going to be the next generation eventually, but it's called mating pool because right now we haven't applied any of the genetic operators, those variation. We've seen initialization, we saw initialization, we saw selection, we saw evaluation, we saw selection. Next is the variation operators. So this is going to be how do we mix up those candidate solutions. Variation operators, I'm probably going to call them genetic operators very frequently. Variation operators is more of a word you would use for evolutionary computation in general. This is a genetic algorithm, which is a very specific type. We can get really nerdy here. There's evolutionary computation, and under that umbrella, there's an umbrella called evolutionary algorithms. And under that umbrella, you have genetic algorithms. And in genetic algorithms, you're definitely calling these genetic operators. Variation operators is a more general term. I might mix and match them by accident. People are really bad with their jargon in evolutionary computation. Anything goes. You just kind of know what people are talking about based on the context. You'll get used to it. So variation operators, some called genetic operators, are used to alter the chromosomes with only selection. The chromosomes are never going to change. Nothing's going to really happen. Eventually, if I let it run forever, it'll just, one chromosome will likely just take one set of zeros and ones, one combination of zeros and ones is probably just going to take over. Nothing's going to ever change. So we're not going to see anything interesting happen. So the variation operators are how we're going to make these things. Like most things with GAs, there's no hard rules on how you do it. Let me take a step back and emphasize. The way we evaluated the chromosomes, I didn't have to do it that way. It made sense to do it that way. I didn't have to. The way I did selection with tournament selection, I didn't have to. If you wanted to do literally just randomly take one, you could do it. It doesn't matter. You just need a mechanism to select. If you think of, I think you should do selection by doing blah, 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 blah. Do it. Try it. I'm just showing you one. The genetic algorithm, the evolutionary algorithms are all just initialize, evaluate, select, variation, repeat until you're done. What those are and how you do them, sky's the limit. Do whatever the hell you want. If you're like, here's an idea, it's probably going to suck, but it's an idea, do it. You never know. Maybe you conclude it does in fact suck. Great, that's fun. The idea of these things, the genetic algorithm, is that simple. I'm only showing you these specific ones because they're ones that you'll see. They're common. But don't think for a second, oh, a GA uses tournament selection. No. A GA has selection. I just happen to pick tournament selection. So it's kind of funny because a moment ago I was talking about those tunable parameters, those hyperparameters. How big is the population? How big do I want that tournament size, right? When you think about it, there's even more parameters, but the parameters are a little bit more, those parameters are very numerical. I want to increase the tournament size, I make that number bigger. But there's more what you might call symbolic parameters or algorithmic parameters, where it's, I'm going to use a whole different selection strategy. That's something you have the choice of tuning, of playing with. So it's not only I envision it like this. If I were to draw here, you could see reasonably well. if here's my GA, here's my initialization, here's my termination, here's my eval, selection, and variation. So init, and in here, there's a bunch of little dials I can turn, right? And then maybe with this eval, there's more dials I can turn. You know, I'll turn the little knobs on there. Same termination, more dials, cell, or var. This one has one dial, this one has one dial, whatever. I can turn those. Those are like changing the numerical parameters. Before I hit run, I can tune these things. Hold on. All right? I can turn these knobs all I want. Or I could also go, no, take this one away. I'm going to take this other variation, call it like var plus, I don't know. Maybe it has two knobs. I just threw that whole variation operator away and put it in a new one, and now I can play with that too. So it's not only the dials, it's these whole like modular things I can take out and do whatever I want with. Is that clear? Or was that, if anything, more confusing? Okay, cool. I've worked hard to try to make this as simple as possible, but please tell me. Maybe I wasn't clear before. You guys are the first to see this version of the course. I completely redesigned it. So going along, if there's anything noteworthy, like feedback you could give me, let me know, because maybe I could, adjust it accordingly. Deal? Yeah? I worked really hard this summer to make it good, though, so hopefully you enjoy it. Okay, like most things GAs, there's no hard rules on how you do variation. Typically, there should be a way to exploit what is already known to be good. And we want to have a way to add some new information to what's already known to be good, to explore the search space a little more. So there's a part of the search space we know is good. Like if the best solution is 1, 1, 1, 1, 1, 1, 1, 1, and I have some solutions that's like 1, 1, 1, 0, 1, 1, 1, 1, and 0, 1, 1, 1, 1. Those are good. So I should look for solutions close to those ones. But I don't want to just exploit what's good. I want to make sure I'm also able to look at other parts of the search space. Not just this one little part around the good solutions. I want to make sure I have a way to actually look at more solutions. And we'll see an example of why this is very important. Crossover. This is another word that they stole from biologists that actually has a really bad analogy, but crossover. Crossover is the variation operator that acts on 2 chromosomes. You could make some that act on 3, 4, 5, whatever, but typically crossover almost always is done to 2 chromosomes. The idea behind this is if 2 candidate solutions are relatively good, maybe if I mix them together somehow and pull them apart, maybe I'll get something that's also good. Maybe even better. Probably worse, but it could get better. If this is good and this is good, 2 unbelievably beautiful people have a kid, the kid's probably going to be beautiful, right? That's the idea. Right? 2 tall people have a kid, the kid's probably going to be tall, right? That's kind of the idea. We want that. Exploit what we know. There's no correct way of doing crossover, but here is a very simple crossover. It's called one-point crossover. Given 2 chromosomes of length whatever, randomly select an index, and then exchange the values of everything between the chromosomes after that index. So here's a little visualization. Assuming I picked index 2. See the little arrows pointing at index 2. This chromosome, for visualization purposes, just have zeros. And the other one has ones. So these are the 2 parent chromosomes. Index 2 is the crossover point. So everything from index 2 to the end is exchanged. Pretty simple, right? It should be. That's it. It's possible that index 0 was hit and then everything is exchanged. That's possible, whatever, nothing really happens. It's fine. It's possible the last one, only one thing changes. That's fine. But this is the idea of crossover. Any questions about this one? I want to emphasize again, this is just one crossover. This is not the right way to do it. There is no such thing as the right way. There are wrong ways, but there are a bajillion right ways. And you are very encouraged in this course to just try weird shit and see what happens. Yeah?
So this is just one kind of crossover, and crossover is just one kind of variational principle. Okay.
Now, I'm going to simplify it though. Usually, you only have two types of genetic operators, variation operators. Crossover and mutation. So crossover is one half, mutation's the other half. Also, typically, this is not a rule. It is very common, if I have 1 point crossover, I'm only going to use 1 point crossover when I hit run. I'm not going to have like 20 crossovers that could randomly be selected to do the variation operators at each loop. I could. There's nothing saying that that's wrong. But typically, it's very common where you just pick, I'm using 1 point crossover for my crossover, and that's just what it uses. You could have a billion if you really want, but for simplicity, just leave it at 1. Yeah. There is reason why you might want to actually change which ones are used throughout the course of evolution. There is motivation for doing that, but it can get a little bit complex. Any other questions about this crossover example? Whoop. Okay, raise your hand if you are absolutely 100% like, yeah, you're following along, I'm happy, this is cool, I'm not concerned. Okay, I know we haven't seen anything running yet. I know, that's normal. But that's all, like each piece of code here should be very bite-sized and simple. It's designed that way. These algorithms really are that simple, and I think I did a good job at making them as simple as I can for communication purposes. Like I said a moment ago, this is the first time it's been redesigned. So if there's a big like jump in like, well, what? Tell me. Because you've probably identified a gap that I didn't, and I can improve it. Okay, deal? Please, listen, yeah? Okay, here's 1 point crossover. Most of this is just my description. Parent 1, parent 2, index int, and it returns a tuple of the two parents. So, who here knows what I mean when I say side effect? This is not so much about evolutionary algorithms. This is more of a programming concept. Who here knows what a side effect is? Y'all should if you took 161, but you may have forgotten. Once I explain it, you might be like, yeah, okay, I know what that is. A side effect is when your function modifies something somewhere else in the code. Pure functions take values, do stuff, and return something. An impure function, a function with side effects, might take 2 lists as parameters, as arguments. But remember, when you give a list to a function, do you give the list to the function? No. You give a reference to the list as a function. So if you're my list, and I got a reference to you, and I say, hey list, raise your hand. Raise your hand. But like, I really am not supposed to be screwing with you. I've messed with him. I had a side effect. That can be intentional, that you can code that way. Typically, people discourage that because it's very prone to being buggy and just creating more complexity in your programs. It's better to have pure functions. What I'm about to say is, this takes 2 parents. You could implement it such that this function doesn't return anything, and it just modifies those 2 parents, like in place. But that's where things can get confusing and difficult. Instead, what this is going to do is it's going to take the 2 parents and the index that the crossover point is. Just got some exception checking here. If the length of the chromosomes aren't the same, we're going to have a problem. If the index that you give it is less than 0 or greater than the length of them, it's just going to index out of bounds, whatever. Otherwise, I make copies of the parents. And then this is a very fancy Python way of doing that exchange. And then return the two children, children 1, children 2. So I made copies of the children, and then this one line of code says, child 1 from the index to the end, you become child 2 from the index to the end, and child 2 from the index to the end, you're going to be equal to what child 1 is at the index to the end. And when you do it like this, you don't need that third variable for exchanging. It's the same idea as, let me go to Colab. The only reason I'm emphasizing this is I don't want the Pythonism to throw you off. You know how if I have like a equals 5 and b equals 6, and I want to exchange the values between them, I need that separate variable, temp equals a equals b equals a, right? What did I do wrong? There. I do not know why I wrote 1. That made no sense. There was no reason it should have been there. But you know, like this is the traditional way you exchange values and variables. You have that third variable. And the reason is if I didn't, and I just said a equals b equals a, well now I just obliterated it, right? Let me show you. Just to be clear, they're both 6. Why? Well, a was 5, a now became 6, so a is 6, b becomes 6. Well, hold on, you know, I overwrote what was an a. It's like, if I want to exchange things in my hands, right, I have to do that. That's what this code does. Because as soon as I go like this, right, I lose it. So in Python, Python's neat and has, who's here has heard this word before? Because if you haven't, you should have, but if you haven't, it's your prof's fault. Syntactic sugar. Who here has heard that word before? Whatever. It's a really corny way, but it's a phrase you'll hear. It's a really corny way of saying when the syntax of your code is just like, like it just makes what you're doing like so elegant and beautiful. Python has some really great syntactic sugar. So here is some syntactic sugar for doing exactly what I just showed you. A, B equals B, A. Here. Get rid of temp. There. All right. If you didn't know, now you know. All right. So isn't that handy? Now, I don't know how often this is actually going to be that useful to you, but in Python you can do this. And this is syntactic sugar. At the end of the day, the computer's doing the same thing, but it hides a little bit and it's just got some nice syntax for it. That's all. Syntactic sugar. That's all that is. All right. So here, if we go look at crossover, I've got 1-point crossover. See, that's what I'm doing there, except I'm also doing it with the slicing. Who here, raise your hand if you are familiar with slicing in Python. Really high, I want to see. You're not. Okay, you're normal. Let me very quickly show you what slicing is, because I don't want anyone to get confused. If I have A equals 0, 1, 2, 3, 4, 5. Actually, no, let's use letters. A, B, C, D, E. Print A. I see A. So far, so good. If I say print A at index 3, I get D. Why? Because it's at index 0, 1, 2, 3. Right? So far, so good. Yeah, we're happy. Slicing is the idea of go to index 3. No, go to index 2 to 5. And it'll actually make a copy of the list from index 2 to 5 exclusively, meaning it doesn't include the thing at index 5. So 0, 1, 2, 3, 4, well, I guess there is no index 5. Let's, for demonstration purposes, let's add the f, right? So it includes 0, 1, 2, 3, 4, but not the 5. That's slicing. And if you ever see a slice that doesn't include an end index, it means just go all the way to the end. Similarly, from the start, go to index 2. Does anyone know the secret third thing in the slice? It means count by 2s. So A, skip B, C, skip D, E. Now I'm just showing you slicing. But slicing is a way to extract and copy, like make a new list of that sublist that you've specified with the slice. So going back to here, this says child 1 at index all the way to the end, you become what child 2 is starting at the index all the way to the end. That is going back to here now, index all the way to the end, exchange. Yeah? We're happy? We're good? Awesome. Okay. 1 point crossover, great. So that'll just exchange information between the parents. Cool? Any questions at all? Please ask. It's really boring to just talk at you. My course notes aren't this good that you don't have any questions. Come on. All right. All right. All right. So this function only returns 2 chromosomes, so we got to run it multiple times. Now, typically, what you'll do, so notice that the crossover is applied to adjacent candidate solutions within the mating pool. Yeah. So there's a couple things to note. One, this loop is going to loop over all pairs of chromosomes in the population. Because I'm lazy, even if you go to like the actual code, no, where's my GA max bit string? You'll see a comment in the population size. It must be a multiple of 2. This is why, because I'm super lazy. If I made it 1, it wouldn't work. So I just added a comment and said, make it 2. And if you don't, it's your fault, not mine. Okay? I'm going to look at pairs of things in the mating pool. I did all that selection, randomly selected things and put them in that mating pool in some order. The order that they're in doesn't matter. When I'm doing crossover, I'm always going to do crossover on whatever I is and I plus 1. So I'm always going to do it on adjacent things. The fact that they're adjacent is entirely arbitrary. You could randomly pick whatever you want within that. I just wanted to do the adjacent ones because it's easier. Start at the beginning, do the first 2, then the next 2, then the next 2, and so on. I also have this here. So, okay, first for I in range 0 to the population size, counting by 2s. So I will go 0, 2, 4. And the reason we want that is because mating pool at index 0 and mating pool at index 0 plus 1 is 1. Then it would be 2, and 2 plus 1, 3, and so on. So it's always the adjacent pairs. So far, so good. We've got this here. If random, less than crossover rate. We don't always apply crossover. There will be a probability to apply crossover to each pair. So I selected 2. They're in the mating pool. Now I'm going to roll the dice. And depending on where the dice lies, I may or may not actually perform crossover on those 2. If I do, they get changed up. If I don't, they're left alone. So we don't actually always want to do it. For those of you that don't know offhand, this function returns a random value between 0 and 1, a floating point number. Crossover rate will be a value between 0 and 1. If I set it to 0.7, I've got a 70% chance of doing crossover because if I randomly pick a number from a uniform random selection, if I randomly pick a number between 0 and 1, there's a 70% chance it's going to be less than 0.7, right? So that's what this is, a crossover rate. And what this is, it's set by us. Typically, you see values like 70, 80, or sorry, 0.7, 0.8, 70, 80%. That's common. There's no rule, though. The rule is use whatever value gives you a good result. What value works good here? Use whatever one works good. Turn that dial until you're happy. Okay, crossover point. Pick a random integer between bit string that exists within the length of the chromosome. That's what that is. So pick a random index for the chromosomes, and then do 1 point crossover here with the thing at mating pool index I, thing at mating pool index I plus 1, its neighbor, and whatever that crossover point is. And then when you're done, that returns the 2, and the mating pool at index I becomes whatever the child is, and whatever that child is. If we roll the dice and we don't perform crossover, they're left alone. They're not changed. They're happy to be the way they are. Cool? Cool. Cool. Now, you might be wondering, why on earth, like look, let's go here, where's 1 point crossover? 1 point crossover. I gave it the index to crossover. Why didn't you just, within that function, randomly pick the index? Why did you randomly pick the index and then give that value to the function instead of just calling the function on the 2 parents and then have the function randomly pick the index? Seems like you've done extra work. Like, why don't you make that, you can make that 1 point crossover more like complete by letting it deal with the random number selection as well, right? If you were wondering that, there's a reason for doing it this way that has nothing to do with evolutionary computation and everything to do with program design. This is an example of something we would call like dependency injection, kind of. Where, look, 1 point crossover right now doesn't depend on anything sophisticated. It depends on just lists, which are just like native Python things, values, indices, and whatnot, and a couple of operators. If I made it have to use the random library, suddenly that's a dependency. Suddenly this needs to manage the random. There's nothing wrong with that, but it becomes a little bit harder to test and can be satisfied that it's like correct. So we do this thing where, like, I didn't write the random, right? So I'm assuming it's correct, but I wrote 1 point crossover. If I use random inside here and something doesn't work, I'm now like, where's the issue, right? But if I just inject the index into it and it doesn't work, like, okay, I know there's an issue with my stuff. And for those of you curious, if we go and look at the unit tests, crossover. No, that's order. 1 point crossover. I was able to hard code for my unit tests for this the fact that, okay, do crossover at index 0 and then 2 and then 3. Imagine trying to test the result where it's got randomness involved. Like, okay, here's the two parents. In order for me to know if you're right, I need to expect to see this. Well, hold on, that function has randomness in it. How am I gonna, like, what? How do I, what? So this eliminates the need to deal with that. There is a way to do that called mocking. You can mock the random library and tell random what to return. for the sake of your tests. Or you could remove the dependency and you're fine. You don't have to deal with it. So that's just a little bit of a programming aside. If you're happy with what I said, great. If you're confused by what I said, it doesn't matter. I'm just FYI. Okay, crossover rate. Crossover is not always applied, thus this provides a way to select candidate solutions to persist in the next generation unchanged, right? Which makes sense. If two things were selected, they were selected because they were good. We don't always want to mess them up then. If they were good, they're good. Maybe give them a chance to just kind of exist in the next generation. The probability of crossover is defined by a hyperparameter called crossover rate. The value would be between 0 and 1. You often see like 0.7, 0.8. But again, if 0.2321 worked for you, great. So here is a potential problem. We just talked about 1-point crossover. And let's say this is our population. And within that population, I actually have two pretty darn good candidate solutions. So this is an example where my population size is 1, 2, 3, 4, 5, and I'm doing bit strings of length 1, 2, 3, 4, 5. Arbitrary values. This is just for demonstration purposes, to visualize. So if you're looking there, I've got two really good things. But you will notice at index 1, there does not exist a 1. Because of this, no matter how I apply crossover, I will never, ever, ever, ever get the best answer. The best answer is 1, 1, 1, 1, 1. I can do crossover, I can do this 1-point crossover on any combination, every single possible combination of parents. I could run this for 1 billion years. I'm never ever going to get a 1 in index 1. Meaning this population is doomed to never be the best it could be. And that's because all it's doing is exploiting what's already good. Currently, there's no way to add a 1 there. There's no way to add new information to this population, to any chromosome in this population. So we can never find the best optimal solution through crossover alone. All crossover can do is transfer existing information between what's already there. We can never add anything new. So this is where mutation comes along. Mutation is a variation operator that acts on a single chromosome at a time. And it's basically the way we add new information to the candidate solutions. Like crossover, there's no right way to do it. Do whatever the hell you want. Hopefully it works. What's correct is what works. What's more correct is what works better. But there's no right way. There's just wrong ways. Here we'll do what we call, because this is a binary representation, the information is encoded as 0s and 1s. We will do a very simple bit flip mutation. So here's what we do. Given a chromosome, select some arbitrary index and then flip the bit, whatever it is. If it's a 0, make it a 1. If it's a 1, make it a 0. Bit flip mutation. So if here's our chromosome, remember mutation acts on a single parent. Pick an arbitrary index. I randomly selected index 2. Doesn't matter. It was a 0. It became a 1. If it was a 1, it would have become a 0. That's it. That's all it is. So looking at bit flip mutation, I just have the exception. I've got the parent and I've got the index I'm doing the flip at. Check the exception. Make a copy. By the way, for those of you not familiar that just learned a little bit about slicing, this right here is basically say copy the list from everything at the beginning of the list all the way to the end of the list. If you just have the colon in there, if you don't specify any indices on either side. This is a quick and easy, dirty way to just make a copy of the contents of that list. Then this right here is a fancy, I could have done it with an if statement. If 0, make it 1. If 1, make it 0. But I just used fancy arithmetic here to do the bit flip. Basically, if child at index is 0, I add 1 to it. So what's 0 plus 1, everybody? 1. And then what's 1 mod 2? 1. And for those of you that forgot what mod is, what is 1 divided by 2? No decimals allowed, only remainders. What's 1 divided by 2? Say 0. And what are you left over with? Yes, very good. Well done. You know arithmetic. Now let's change it. Let's say the value at child at index was 1. So what's 1 plus 1? Everybody? 2, I know. And then what's 2 mod 2? 0. Why? Well, what's 2 divided by 2? Thank you, Cole. 2 divided by 2 is in fact 1. Remainder? 0. There you go. Look at this very sophisticated mathematics to turn 1s to 0s and 0s to 1s. Great. And at the end, return the child. Huzzah. Similar to crossover, we also have a mutation rate. Here, we don't need to get fancy with our indexing with the loop because they don't need to be applied to pairs of chromosomes. We are doing it just one at a time. Each chromosome has a probability to have mutation applied to it. So for each chromosome in the mating pool that may or may not have already had crossover applied to it, although there's no rule saying you have to have crossover applied before or after mutation. You can do whatever you want. I always just do crossover, then mutation, because whatever. So for each chromosome in the mating pool, roll the dice. Do I mutate you? Yes or no? Roll the dice. Mutate, roll the dice, mutate. That's what's going on. If I do, randomly pick an index of whatever the length of the chromosome is, and then mating pool at that index, mutation point, and then make mating pool at that index the result. Because remember, it didn't have a side effect. It made a copy of the chromosome and changed that and returned it. It's a pure function. Yay, we like that. Cool. So your crossover rate, just like, your mutation rate, just like the crossover rate, is going to be between 0 and 1. Usually, crossover is going to be, mutation is going to be a much lower number than crossover. Usually, you're looking at like 10, 20%. Some people don't do it at all, which you saw a scenario where that's a bad idea. Some people have to crank it up depending on the problem you have. Sometimes you need to have a mutation rate that's really high. Some people will make it so as evolution goes on, you crank mutation rate more. Maybe you lower crossover rate over time. Whatever. You can do, again, whatever the hell you want to do. As long as you're following the basic framework, you're doing a GA. Cool? Cool. And then termination. That right there was a description of a single step. We did initialization. We evaluated, selected, variation operators, crossover mutation. That mating pool, after everything was done, well, that's now the new generation. Evaluate it. Select, genetic operators. Evaluate, select, genetic operators. Do that over and over and over and over and over and over and over again. But when do we stop? I don't know. When should we stop? Usually, for me, what I usually do is I just have another hyperparameter and say, I want you to run 10,000 times. Some people will say, I want you to run until I find the best solution. That can work sometimes. I want you to run until you've converged, until the population's diversity level drops below a certain point, meaning nothing's really going to change anymore. I want you to quit after nothing really, like since when the best chromosome is above some certain threshold, when it's good enough. When no learning has happened, the population is relatively unchanged for some number of generations. Whatever you want. For me, I like the simplicity of just run this long. But of course, that has problems, because if you tell it to run 1 million generations and you come back in 2 days, and you look at the result, and you see that it clearly wasn't done, you're like, shit. Crank it up to 10 million and come back in a week, right? Kind of annoying. But this is easy. So here's what we got. This right here, I'll show you here. Within this code, you'll see these little like tags, these comment tags I have. Ignore these. I mean, they're useful in the sense that you can read it and be like, oh, this is the crossover bit. But they're really just there for when I import the code into the website, it gives me a tag on where to say begin and end. So they're not too important. You don't need those or anything. So here we go. Assuming initialization is already done, here's that generational loop. Empty list population fitness. For chromosome in the population, calculate its fitness. We already saw that above. This right here is just some bookkeeping stuff. I've created a list just to keep track of what the best fitness was for each step of the generation, what the average fitness was for each step of the generation. You don't need this. I'm doing it for bookkeeping. Mating pool. This is selection. Fill up the mating pool. Do crossover. Do mutation. And then make the population what the mating pool was and repeat. When do I end? When this loop ends. When it hits the number of generations. It's evaluation, selection, variation operators over and over and over. There's bookkeeping stuff, ignore the tags. And once it's done, we'll do one last evaluation because you figured the loop ends by applying the genetic operators. So we did fitness evaluation. Then we did one more application of the genetic operators, so they've changed. So when the loop ends, we'll do one more evaluation, and then we can look at the results. And we'll do that whenever next class is. All right, see you later.